Yeah, so I'm super happy to receive this award, and I thank CAIAC and the Educating Committee for selecting this work. I would also like to thank my thesis supervisors, Rupam and Martha, my current supervisor, Chava, and my collaborators, Samuel and Yangjin. All right. So first, I'll give a quick example to motivate this problem. So consider the example of autonomous driving. So you're trying to learn how to drive a car, and the main problem is that of non-stationary environments. So imagine that your driving agent, it learns to drive the car on a nice road in a city environment, and then it drives into an off-road condition. So ideally, we would want this agent to quickly adapt to the change in the environment. So for instance, it might need to learn how to drive with muddy tires. Now, current methods, a lot of them, they are unable to adapt to such a change in a timely manner. So here I show the performance of a softmax policy gradient algorithm. So so imagine this is the road condition and say this is the muddy condition. So until this non-stationarity, it has a good performance. So it learns to get a good performance. But after this change, its performance drops drastically. So to alleviate this problem, we introduce what we call as the alternate policy gradient estimator, and it it really improves the performance, as you can see in this curve. So before the non-stationarity, before the change in the environment, both the methods, they have an equally good performance, but after the non-stationarity, the regular method, it's unable to adapt, whereas the alternate method, it adapts well. Okay, now I can get into some more details. So our goal is to learn control problems, which is how to learn a good behavior which can achieve a given goal. As a running example, I'll use this task, which is called as mountain car. So the agent has to learn how to drive this car up to this goal state. And the car is underpowered, and the agent can pick either action left, right, or do nothing. So you can imagine the optimal policy would look something like this. Agent would try to go left, right, and finally it reaches the goal state. And I'll be talking about reinforcement learning class of solutions. So RL uses MDPs to model control problems. So you have an environment. So this is your world. This is the learning agent, and the environment gives the agent a state and a reward. And using this state and a behavior called the policy, the agent samples actions which it gives to the environment. So for instance, in mountain car, you start in this middle state, then you take an action towards right. So you move right, and then you take an action towards left, you move left, and agent at each time step gives you a reward of -1. Now in reinforcement learning, the goal is to maximize the sum of rewards that the agent receives. So in this case, I'm receiving -1 at every time step. So if I were to maximize the sum of rewards, I should learn how to reach the goal state in a minimum amount of time. Okay, so I'll be talking about policy gradient methods, which are super popular and successful. They have had real world control applications and also large scale, they also work well in large scale simulated games. The goal in RL, as I told you, is to maximize the sum of rewards that the agent receives. And we denote this by JPy. So this is the objective that you're trying to maximize. And policy gradient methods, they consider a parameterized policy pi w, parameterized by these weights w, and it learns these weights by doing a gradient ascent on the objective JPy. That's policy gradient. You do a simple gradient ascent on your objective, and then you can have different optimizers. You can change the objective a bit. In this work, I'll focus on softmax policy gradients. So softmax policies, they are super popular. Uh, I think they're the standard for discrete action cases. So when you have discrete actions, people usually use softmax policies, and this is a softmax policy where theta is called the action preference for a particular action. and it's updated via stochastic gradient descent. So instead of having the true gradient here, we use an estimator, a gradient estimator, such that its expectation is equal to the true policy gradient. So I'll denote this estimator using G. Okay. So the problems with the regularly used softmax estimator, so this is the regularly used softmax estimator, is that it is unable to overcome non-stationarity in any reasonable amount of time. So we propose this alternate estimator, which is its expression is a little different, and it is able to achieve better performance in non-stationary environments. Okay, let me show you both of them on a single slide so that you can see the difference. So the regular estimator, the top one, has the gradient of this log pi term, whereas the alternate estimator has the gradient of the action preferences. And pi is obtained from action preferences using softmax function. So just this small change, and this allows the alternate estimator to work well in non-stationary problems. And the reason for this is that the alternate estimator, it becomes biased when you estimate this value function v pi. And it can then utilize this bias to overcome non-stationarity. I'll explain this a bit more now. Okay, to explain it, I'll use the simpler case of a bandit task. So imagine you have 3 arms and you need to learn which arm is the most beneficial. So each time you pull an arm, you get a reward. So for instance, if you pull arm A0, you get a reward of 1. If you pull arm A1, you get a reward of 2. For this last one, you get a reward of 3. So eventually you should learn to pull this third arm always. And I'll be showing you a lot of plots on this triangle. This triangle is the policy probability simplex, or the policy simplex, and each point represents a policy here. So for instance, the center point is the uniform random policy. And on this top corner, you have a policy that picks action A2 with a probability of 1 and receives a reward of 3. This is a reward of 1 and this is a reward of 2. And this area is called the saturated region, where the policy picks a particular action with a high probability. So you can see in this region, policy would be picking A1 with a high probability. So what happens is, say you start with a uniform policy, and these arrows, they show your gradient updates. So say you start with a uniform policy, and slowly you will move towards this top corner, which is your optimal policy. And when it reaches the optimal corner, it also saturates. It reaches these corner regions. Now, after non-stationarity, imagine that after non-stationarity, this reward becomes 2, whereas this becomes 3, and this becomes 0. So your policy is saturated in this corner, but the optimal corner has changed to this point now. And the regular softmax estimator, it won't move towards this corner in a reasonable amount of time. So non-stationarities, they create a problem for the regular estimator because the policy saturates, and regular estimator is unable to work well with saturated policies. To show you an example, so consider this corner. So say you are in this corner. Now you can see the regular estimator, it has extremely small updates. The length of this arrow is super small. So that's why it takes a lot of time. Whereas the alternate estimator, you can see it has the update magnitude is super large. So it will quickly move out of the saturated region towards a uniform policy. And from there, it can then move to the optimal corner. Okay, this B is similar to the value function v pi. So I'm showing you the case when the value function is optimistic. So recall that the rewards are 1, 2, 3. So a value function of +4, which is greater than all the rewards, is optimistic. So with an optimistic baseline, optimistic value function, the alternate estimator, it pushes the policy out of the saturated regions. And this is what helps it escape non-stationarities. Okay, this learning curve again. So with the regular estimator, say right at this point, the policies, they are both they're saturated, and the regular estimator, because of small gradient magnitudes, it's unable to move. Whereas the alternate estimator, it quickly moves towards a more uniform policy, and from there it can move to the optimal policy or the optimal corner. To corroborate this, I show you the entropy plots for the policy. So for the regular estimator, you can see that the entropy does not increase, so it remains small, which means the policy is saturated. Whereas for the alternate estimator, there's a jump in the policy entropy right at non-stationarity. Yeah. Okay, to conclude, the alternate estimator is simple to implement. As I showed you, it's just a small change. And in autodiff packages, it's super quick. It's like a two-liner change. It can be adapted to work with various policy gradient algorithms and works well with different function approximation schemes, such as a linear policy or a neural network policy. And in our experiments and some theoretical analysis, we show that it is superior or competitive to the regular estimator for both saturated and uniform policy initializations. And to conclude, it makes existing PG methods more viable for certain non-stationary problems, and by extension, practical for many real-world control tasks. That's the end of my presentation, and I'd be happy to take any questions. And for further details, you can either look at my thesis, or we also have an associated publication.
Thank you very much, Shivam. Thank you very much. Does anyone have a question to Shivam? You can raise your hand or raise your hand physically with the camera. I think I saw one hand. Ian?
Oh, sorry, I was applauding.
No problem. I'll just check again. Sure, Jacob can do it better. But Shivam, I have a question. I don't see any hands. If you see Jacob or Maker, is your estimator, alternate estimator, is to be used to replace the regular one or in combination?
In this work, we looked at a replacement. Obviously, one easy strategy to use it in combination would be to just regular plus alpha, or alpha 1 minus alpha alternate. In this work, we exclusively looked at it as a replacement. Uh, I have not studied this combination properly. So this is one way. Another way could be, so there's some another formulation. So if you tweak the terms, you can, like, instead of just this alpha, you can have this alpha as the entropy of the policy. Like, there are some ideas, we haven't investigated them, but interestingly, for the problems that we tried, alternate estimator was much better. Although I think the regular one would be good in certain situations as well, but I think more analysis is needed.
Wonderful. Thank you. Thank you, Shivam. I don't see any other question. Is that right?
I have one.
Oh, go ahead. Sorry.
So, in what type of problems you tested these changes?
So I tested it in, so first is you start with a uniform policy. So I tested it with bandits and MDPs. In bandits, I looked at tabular bandits with 3 arms. For MDPs, I looked at simple environments. So I looked at mountain car, cart pole, and linear chain. And I looked at tabular, linear policies with tile coding, and neural policies. And also we looked at a simple reacher task where there's a dot and it has to reach a certain target. As for non-stationarities, right, so we studied problems with uniform policy initialization with the and then if your baseline is pessimistically initialized or optimistically initialized. Right. Okay, so this is reinforce on linear. And this is the uniform initialization. And alternate is still better. Expected is the best, which makes sense. And then, yeah, these are, oh, sorry, I didn't have carpool, I had acrobot. And this is with linear policies. So to summarize, it alternate works well if you have a uniform random policy, and if a uniform random policy does good exploration, or it works well if you have non-stationarity, and after the non-stationarity, your baseline becomes optimistic. So if your baseline becomes pessimistic, then alternate is in trouble. So if your baseline is pessimistic, such as -4 here, then say you are at a saturated region, it will saturate you even more. So in certain scenarios, in particular, uniform policy, when uniform policy is good for exploration, or in a non-stationary environment where after non-stationarity your baseline becomes optimistic, I'll say alternate is really good, at least with the at, at least for the problems that I tried. For bandit, it's like awesome compared to the regular in these two cases.
Good. Thank you.
Thank you.
So Renata, do you want me to introduce the next?
Yes, please.